To build anything complex, you need precise measurements. Yet software engineering relies on a standard that changes size depending on who looks at it. For decades, the default for estimating project scope and complexity has been lines of code, or LOC. But LOC is volatile. The exact same software application will yield completely different line counts depending on the programming language chosen, or even the individual coding style of the developer. We see this instability in backfiring data. Translating one unit of pure functionality, one function point, yields wild results. In C, that point requires 128 lines of code. In C++, it drops to 53. In Smalltalk, it takes only 30. Imagine sizing a physical structure this way. If the measured length of a suspension bridge changed by a factor of 4 depending on who poured the concrete, the blueprint wouldn't be considered a valid engineering standard. Sizing software by counting lines of code is like sizing a building by counting the bricks. It measures the raw material, syntax, rather than the actual architecture and volume of the system. To accurately estimate and manage a software project, engineers must measure its dimensions independent of syntax and formatting. We can achieve this by dividing software measurement into two distinct perspectives, the macroscopic and the microscopic. The macroscopic view focuses on the problem space. This represents exactly what the software must achieve for the user, regardless of how it is coded. The primary metric for mapping and measuring this problem space is the function point. The microscopic view deals with the solution space. This evaluates the actual algorithmic density and complexity required to execute those tasks. To calculate the volume of this solution space, we rely on Halstead's software science. Function points measure the system from the outside in. Halstead's metrics measure it from the inside out. By combining these two models, we can mathematically describe the size and complexity of a system throughout its lifecycle, long before and after the code is written. Function point analysis starts with the information domain. We count discrete interactions rather than lines of code. Let's use the Safe Home security software to see how this works. First, we define a strict system boundary, the dashed line separating the user and the external environment from the internal software. Next, we observe how data moves across that boundary. Every piece of information flow can be categorized into one of 5 parameters. The first is external inputs. These are interactions where the user provides data or control information to the system, like entering a password or pressing a panic button. Second are external outputs. This is information the system sends to the user, such as an alarm alert or a sensor status message. Third are external inquiries. These are direct queries that require an immediate response, like checking the status of a specific security zone. Fourth are internal logical files. These represent the logical groupings of data maintained entirely within the system's boundary, like configuration settings. Finally, we have external interface files. These are data sets that reside outside our boundary, but are referenced by our system, such as external sensor logs. Mapping these parameters requires no knowledge of the underlying programming language. Identifying these 5 parameters gives us a quantifiable measure of exactly what the software delivers to the user, successfully sizing the macroscopic problem space. Gathering the raw counts is only the start. A complex internal file requires more engineering effort than a simple input button, so we have to apply complexity weights. To do this, we use a computation matrix. The 5 parameters make up the rows, while the columns assign weights based on whether the interaction is simple, average, or complex. Organizations use specific criteria to categorize these counts. We take our findings from the Safe Home architecture and populate the matrix. We then multiply the raw counts by their weights. A simple input might be weighted at 3, while a complex internal file could be weighted as high as 15. Summing these weighted subtotals gives us the base count total. To reach the final function point metric, we apply this equation to our total. The second half of this equation is the value adjustment factor. This factor accounts for system-wide characteristics, such as distributed processing requirements or high-performance constraints that affect the overall engineering effort. This calculation can be completed during the architectural design phase, months before coding even begins. Function points allow engineers to forecast scope and effort from architectural blueprints, providing a more stable foundation for estimation than counting lines of code. While function points size the architecture, we can objectively measure the density and complexity of the code itself. This brings us to the solution space. Maurice Halstead proposed that all software can be mathematically modeled by breaking it down into fundamental primitives. Halstead's theory is that all code consists of two things: operators, the actions or verbs, and operands, the nouns or data points. Operators include keywords, math symbols, and logical gates, the if statements and plus signs that drive the logic. Operands are specific data being manipulated, like a password variable. We extract 4 variables from the code: the number of distinct operators and operands, and total occurrences of each. These variables form the program volume equation, which calculates the raw information volume of the algorithm. By differentiating between the total count and the distinct vocabulary size, this equation captures the true complexity of the algorithm structure. Halstead's volume bypasses formatting and syntactical bloat. It isolates the information density of the algorithm in bits, giving us a microscopic view of code complexity. We now have a 2-dimensional framework: macroscopic sizing via data flow and microscopic sizing via algorithmic primitives. Function points are calculated early in the project lifecycle, specifically during the design phase. Halstead volume is measured later, once the code exists. These early macroscopic calculations help managers predict total effort and person months before development starts. Later, the microscopic volume calculations help engineers target high-risk modules for more rigorous testing. This framework offers a predictive, multi-dimensional view that simple line counts can never provide. For engineering students and professionals, the goal is to move beyond language-dependent measurement habits. Adopting these mathematical models of functionality and volume represents the critical transition from intuitive estimation to evidence-based software engineering.